we are going to begin with problems. Problem 1. Yes, so any problems in matrices, ideally from this Artin or in general also if.
1.5, that question.
Okay, so the first 4 are okay. First 4 are just yeah. Okay, 1.5. Yeah, this is yeah. So ABC be matrices of size, respective size. So I'll write it. So this is 1.5. So A, B, C. So this is L cross M, and B is M cross N, and C is N cross P. Then what are they asking? How many multiplications are required to compute the product AB? Okay. So how many multiplications, number of multiplications to compute AB? Any ideas? Okay, then I will say. So it's not difficult because basically you have to just know what is the multiplication definition, and then we have another one, right? So what do we do, right? To find, so in the product, right? So this is a product. How do you find the 1,1 entry of this? How do you find that? Like, according to the rule?
First row in uh, first row into the second matrix's first column.
That's it, right? So then that's easy, right? So when you do this, so when you do R1 times C1, since we are doing the first problem, so let us write, okay? It is just 1, 1 times B11. So B11 means 1,1 entry of B. Okay. And then there is A1 to B21. This is something that all of us know. Sorry. And then there is Bn1. Okay. So how many multiplications you needed? N, right? It's in front of us, right? N multiplications, isn't it? 1 multiplication, 2 multiplications. No, it's not N, it is M. Sorry. So already first error. M multiplications, right? M multiplications. So to find each entry, to find 1,1, you need M multiplications. So you will write to find ijth entry, how many multiplications will be needed? M. Why will it change? Right? So what do we have, right? Our conclusion is, you see, I'm not doing anything. I'm just telling you the rule and just unpacking it, nothing, right? So for ijth entry, M multiplications needed. So what will be the total number of multiplications needed? Just the number of
L into
entries.
M into N.
Yes, right. Because there are L times N entries, right? This dimension is L cross N. Right. So that many entries are there. So number of entries is also L times N. So L into N into
M.
It's a nice answer, right? So this is suggesting a nice thing that that the final, no, yeah, that if you look at this, yeah, the answer only depends on these things as a set, L, M, and N. It doesn't depend on the exact, whether if it was, you can already understand it. If it was M cross L and this was L cross N, still the answer will be the same. That's the nice thing. So it only depends on, doesn't depend exactly on the row and column thing. So this is the number of multiplications needed if you do it in the usual way. Okay, obviously, there are ways to multiply where you need more less multiplications. There are algorithms like disk you can use. I think, yeah, some algorithms. But when they ask the question, they mean that, the usual way, if you multiply, then how many multiplications are needed? Because all these multiplications are not independent, right? They are dependent on each other. So yeah, let's move on. And what I think the next part is more interesting. In which order should the triple product ABC be computed so as to minimize the number of multiplications? I'm sorry, so as to minimize the number of multiplications required. So triple product here, I suppose they just mean the usual triple product. Yeah, because these are matrices, but also for vectors, we have a triple product, right? But I suppose that is not what they are talking about because these are not vectors. Well, these are vectors in some way, but these are not, we are not treating them like vectors. These are matrices for us. So what is this suggested by Gilbert Strang? So Gilbert Strang, he is a very, very prolific teacher. So you can see he has his coursework, right? MIT Openware, Openware or whatever, courseware or something. Yeah, MIT Open Courseware something. He has a course on linear algebra. But linear algebra properly is not in our syllabus, so we should not worry too much about it. But later on, you can watch. It's a very excellent, very helpful videos. So yeah, so triple product just means, yeah. So we know that the triple product makes sense because the dimensions are given correctly. Okay. So, but and then we know that mathematically all these things give you the same answer. Any doubt? We have discussed that, right? These two things give you the same answer. But mathematically, the answer is same. But computer scientists or data scientists, like computational people, they will ask how to minimize the number of multiplications. Should I do the left one or the right one? So the first question is because there's no creativity needed in this question so much so far, right? It's just understanding the question clearly. So is the question clear? In which order, right? By order, you mean these two possibilities. Either you should do the first one or second one. Mathematically, there is no difference in terms of what the quantities are, but we want to compare the number of operations needed. Okay, and among these two options, which one will minimize? So how do you know? Well, we don't know. So let us just carry out the first one and see. Carry out this operation and ask yourself how many multiplications are needed. We have already discussed it. Right? So if you do AB, then how many multiplications were needed? LMN, right? LMN multiplications, LMN, I'll write it, multiplications needed for AB. Now AB is computed, you have spent LMN multiplications, AB is computed. Now you can treat this, if that is more comfortable, you can call it a D. If that is more comfortable, if you don't mind it, then you continue writing it as D. That depends on your level of comfort. Some people can do this thing in their head. That's also fine, right? So now how many multiplications are needed to compute this? Well, that's what we have to compute now, right? D times C. Again, we already know LNP.
LNP.
Right? Shirin, is this okay?
Yes, sir.
right? So when it was this two, you needed LMN. So what we have proved is the general result, right? That if this is the situation, then it will be LNP. If any situation you understand, so basically you're applying the same thing iteratively, right? Like what happens in algorithms, right? You have that theorem and then you are applying it in different situations or in the same situation like 2 times. So this will imply, this will again, you can write it if it's just a subjective, that this will require LNP multiplications. Now what you write it. So in total, how many multiplications are needed? Well, everything is in front of us. There is no problem. This is the total. Now you have to add them. There's nothing, right? Because you did the first one, got the result. Now you're moving forward, right? Yeah. So it's fine. You add them. Now you see what this is. M plus P. Right? And now you can think. Let us think. Let's look at the question. Okay, so if you do it the other way, then how many multiplications will you take? So
You get
MNP plus
LMP.
LMP, right? Is again same thing. You first do the BC, you get MNP, and you get a matrix of size MP, and you again do it. So this will be L plus N. So I don't know, is it even possible to compare these numbers? Which one is bigger?
I think we should choose rows and the row and column so that they're summing, right, instead of being products. Like in the first case, we should choose the matrix with the biggest row and the column as M and P. Should choose those matrices, right? Instead of letting them become product of like L into N.
I do not no. Okay, so I understand what you're saying. So, but the answer will depend on which numbers are bigger, I think, right? Like here, I'm finding the question a little vague, because means that if some specific number is given to you, like that's what will usually happen in your exams, or some connection is given between the numbers, right? That let's say L is this, M is this, N is this, then you can compare, right? Or two of them are given or something like that. So we had the formula, now you can compare, but yeah, so like this, what can you say? Is there anything you can say? So Nagesh, what are you saying? Are you saying that this L is the, so I don't know.
So we have to choose the matrix with the biggest row as L. So that would be A, right?
No, and but I cannot change the order. I mean, I cannot, I don't have that choice, right?
No, if C was matrix with row bigger than A, right? I think we should first multiply AB and then do BC, then the product of AB with B with C, right?
If okay, so when would you do this, as you are saying, in what situation? When, so you want to minimize P and M. I mean, you want to
minimize L plus N.
Okay, minimize L plus N.
Because if L is in the product,
Mm-hmm.
I mean then what you multiply it will also have an effect. But I thought like it should be in the sum. The biggest row should be in the sum. That way it won't.
Yeah, that is right. But then that will depend on whether L and N are bigger or not, right? I mean, yeah, it would depend on L and N, right? I don't understand that. No, there's something vague about this question. So what I'm saying is that depending on L and N, either this can be bigger or this can be bigger. Both can be bigger depending on the values you give. I mean, you can easily write values, right? Where the first expression is smaller, then you can write another 4 values where the second expression is smaller than the first one. Right, so the question is not clear to me. Wait, number of multiple. Just let me see if there is a. I'm just searching it online just to be able to understand the question, right? Mm-hmm. No, I cannot find anything useful. Anyways, I mean, we have done the question as much as I think we can, because beyond this, we cannot say. But then let me ask this. Okay, let's just make the question. So if L is less than M is less than N is less than P, or less than E can be equal, then in which order should you multiply? Then which one of them is bigger, or which one of them is smaller? Is there anything we can say in this case?
That ln into m plus p should be smaller because the L is smaller over there in the condition you gave.
Right. But N can balance it out, right? N is larger, and here N is small, taking a smaller role or something.
Yes,
Right.
because addition is not that much of a problem, but multiplication would
Yes,
be easier.
yes. So see, the reason that you gave, that here this should be taken because L is smaller, but by the same token, this should be taken because N is larger. Right. So there is a kind of there is not clear, right? Let us just try one more thing. Now we are just sort of, if you can comment something on the difference. Mn L minus P LP N minus M. Yeah, so you see, if L is bigger than P and n is bigger than m. If this happens, then you should certainly, yeah, then this is positive, right? And in that case, you should take, which one did I subtract? M and P. Then you should take this, then this one is smaller, right? So you see, there are some things that can be said, but in general, I don't think so, but yeah. Anyway, let's move on. We understand what to do in this kind of question. Now, beyond that, because as I said that, both the expressions will win depending on some conditions on ln and p. Now, asking to come up with all those conditions, that maybe is a, I don't know, vague or extremely difficult. I don't know. So yeah, what more questions should we do? Let's move forward and see. Anyone tried any more questions? Yes or no, you can say. No more? Okay. Okay, I thought you would try more
Yes,
questions.
sir.
Yes, and please say.
The next question,
In this sequence only?
1.6.
Okay.
Yes. That the blank spaces is for 0.
Yes. Yeah. That's the convention.
So the first part is okay, but the second one, like uh,
Mm-hmm.
1 a01 to the power n.
Mm-hmm.
So how to do it n time? Is that for n times?
Yes. Yeah. For any n, and the answer will be in terms of n, right? Yeah. So these kind of questions is when we get a handle on matrices, and need to get this handle over it. This is not a difficult question. So basically, I will show you the mathematician's way, kind of like you will see why I'm saying that. So what is the answer for this? I know we sound silly, we are just multiplying matrices, but still, tell me what's the answer.
1.
A plus B, right?
Yes, a plus b,
That's the cool thing, right?
then
It's A
0
plus
and 1.
then 1, right? And yeah, I mean, one can never get, one can always get better at matrix multiplication, always. I can get better at matrix multiplication because there's so many patterns and insights into matrix multiplication. You can already see there is something nice happening, right? Somehow those two things are getting added when these two things are multiplying itself. So now tell me that this is happening for all A and B. Is this symbol fine for all A? That is, we should be used to all these things. It's not to make our lives complicated, it's to simplify things, it's to get a better language. So for all A and B. So if it is true for all A and B, then how do you get that one from here? I am saying that from here, you can get this one. It is true for all A and B. So what should you take as A and B to get that one?
Yeah.
Just take A and B to be equal. That's the thing. So you have already actually done the question. So Srini, I'm saying that this question is a harder question than that one in a way. Okay, but obviously both are easy. So you will say, okay, since it is true for all A and B, put A equal to B. I mean, this is the beauty about mathematics, right? That sometimes solving harder questions are easier because somehow they are harder in terms of complexity, but they are easier in terms of arriving at the conclusion logically. Okay, so that's one has to understand. That's why the binomial theorem, right? You put x equal to 1, y equal to 0 to get so many different identities. But the binomial theorem is easy to, not very difficult to prove either, right? So that's the thing. So you put a equal to b because you can, and then you get yeah. This is true. And now how do you compute this? Nagesh, can you just tell us how to compute this?
As in what the answer is, or
The steps. I think the steps are important.
so you take the answer from the previous step and multiply. Is that
Okay.
what you mean?
Yeah, that is right. And so we just take this, right? Because that thing is equal to this, and by associativity, we can write it like this. Okay. It's important to note that this is by associativity. So this, and then that's it, right? So then it becomes, this is 1 plus 2a. So now again, applying this one again, where b is 2a, it's 3a. And then, it goes on and on. You know what the answer is. Okay? And obviously, if you have to write a proof, then you have to say by induction. But if you have to know it for yourself, then you don't have to write a proof. You know it is true. It is not like you're making any guess. It is true. We have checked it. Okay? But obviously, you can say by induction, you assume this, and then next step, you again multiply. And so everything is in this actually, and nothing else. Right? Okay. So what you can see here that has happened, and this is a little bit of insight, you can see what is happening here is, so here you look at this collection of matrices. Okay, this collection of matrices is matrices of the form 1 x 0 1, and it's good to again this is not to complicate things. Okay, it is not to, oh, why are we considering this collection? You'll see we leave the benefits a little later. Okay, but you will see even now we derive that special case from the more complicated case. So basically x is in real numbers, and we're looking at this collection of matrices. Okay, so this is what we do, and you will see how the subject becomes like water. This even if you understand these things in a conceptual way. So this is just this, C is just this collection. Now, and the other thing is you look at the real numbers. Okay. Do you see some similarity between these two collections? Is there any similarity you see between these two collections? Means matrices which look like this, for the moment 2 by 2, and this collection. Now, do you see any similarity between these two collections? Yeah. So last time, okay, so you know this from lower grades and so on, that this collection also has an addition, also has a multiplication. But you also know, you knew it always, but I told explicitly that this collection C will also have an addition and a multiplication. Do you agree with me? Right? This also has a multiplication, it also has an addition, and also a subtraction. Okay. Well, no. Okay. Am I correct that this collection has a multiplication and addition? It's important to bend our heads a little bit and think about these things. Okay, not to get uncomfortable here, but try to think about this matter. It will be important, binary operations and so on. So am I writing something correct or wrong? Does this collection have a multiplication? Yes or no?
Yes.
Yes, sir.
Okay. Does this collection have an addition? No.
Yes.
No, we don't have addition. That's what I wrote there is wrong. Yeah, and why I'm wrong is that, and this is very important to understand, that it doesn't have addition. What do I mean by this? Even does it have an addition is sort of a vague question, but it's a very simple question to know whether it's yes or no. And it is just this. If you add these two things, when I say has an addition, the sum should also be in that collection. The sum is not in that collection. Is it in the collection? No. So it does not have this addition, at least the usual addition at least is not there. Some other kind of addition may be there, but we are not going to think about that now. Okay. But usual addition is not there. Again, some other addition may be there, but that we are not interested in right now. Okay, very good. Something very nice is
So
going to
the
happen.
dot is not scalar multiplication, right?
No, that is also a good question, but again, you will see it will not have a
s-
scalar multiplication also.
Means scalar multiplication, basically addition done multiple times.
Kind of, you can say that, yeah, but yes or no, yeah, little bit yes or no is there, but it's not there here. Okay, okay, but this is something certainly which we have. We have a multiplication here, and we have this. Okay, now just to make things easier, let me remove this multiplication from real numbers. Now you look at these two collections. First collection has a multiplication. What that multiplication means, you know very well. Second collection has an addition. What it means, what you know better. It's just grade school mathematics. Now, what is the similarity between these two collections? Well, you will say, first thing is that if you look at this collection, there is a generic element. Generic just means a generic element, English word. This, where should you connect this to? Just X. What else? Is there anything else to connect it to? No, just X. This will be 1. So this is certainly a connection that anyone can see. Okay. But what this exercise is making you learn is the following. You look at this element and you map it to X, connect it with X. You look at this element and you connect it with Y. This is what is called, it's a function, but function not from numbers to numbers, but from some matrices to numbers. No problem, right? It's okay. We understand what's going on. This goes here. Now, if you multiply these two things, then where do they go? If you multiply these two things, then where do they go? They go here, right? Okay. And if you add these two things, then where do they go? Right? By the rule, where does this go? It goes here. It's a complete mirror. Do you see what happened, right? Multiplying in the above world is same as adding in this lower world. There is no difference. Is there any difference? Right? All the information can be recovered, vaguely speaking, right? So you take elements here and you multiply them, and you want to know where the output goes. You don't have to multiply them. You send them to this world and add them, and this output corresponds to that input. That is where it goes. This is what is called a group homomorphism, but again, we don't need that language. Yeah, Shirin, you may recall, this is the kind of a group homomorphism. It's a homomorphism, right? From this collection to this collection, right? So f of this thing, it is very important to understand from this. That's how you will see some people they're very good at matrices. If you see them as numbers, that's what we are doing in this case. We are able to, in this case, life becomes easier. Yeah, you go in this world, and in this world you add, because here it's addition. Here the operation is addition, and they are same, and everything is bijective, complete information. But this is fine. So is this making sense so far? Is it okay? Right. Let us now try to use this quickly. Okay. You now tell me that okay, in C, though I have not formally defined, in C, does every element have an inverse? Multiplicative inverse. Means for this thing, what matrix will you multiply with to get the identity matrix? That is my question. Or is there such a matrix?
Minus X.
Minus X, right? And you can see that because you've already done the exercise that it adds a plus b becomes 0. But also you know that this guy goes here, and in this world we can find the inverse. Inverse of x is minus x. And minus x version, or whatever you want to say in that word, a pre-image to be mathematical in that word is this. And so this must be the inverse of this in that word. So you can use all this information, and this information is a very, very useful. You see, when we do determinants, you can help you to compute determinants and so on. Life becomes easy. Okay, so this is all we did so far. So are we going to do the next questions also, Shireen? 1.7. Hello.
Can we see
Sir,
1.9?
Sorry.
yes, sir. It would be helpful because these types of questions are there
Yes.
in the
Yes.
previous years.
Okay. Yeah. And okay. So we'll do that, but we'll do that after a 4 minutes break. So 4 minutes you can count on your in your clock, and after that you can join. Okay. Then we'll do that. And also Nagesh,
Okay,
what
sir.
you were saying, we'll do. All this we have to do. Otherwise, we won't get comfortable with the topic. It's not a matrix theory is not a joke. One has to do these things. Yeah. Okay.